Brace yourselves for a cosmic cataclysm of unprecedented proportions. Betelgeuse, the red giant star poised on the edge of our galaxy, is sending ominous signals through the universe. Using the James Webb Space Telescope, astronomers have uncovered something profoundly unsettling about this colossal celestial body. As renowned astrophysicist Brian Cox issues a grave warning, the question looms: are we on the precipice of witnessing a catastrophic supernova explosion that could forever change the night sky as we know it? Let's dive in. In the grand tapestry of the cosmos, where stars are born, live, and die in spectacular fashion, one star has recently captured the imagination and concern of astronomers and the public alike. This star is Betelgeuse, a red supergiant of immense proportions and age, situated conspicuously in the constellation Orion. Its distinctive reddish hue and variable brightness have long been a source of intrigue, but recent developments have intensified interest in this celestial giant. As we explore the nature of Betelgeuse, we find ourselves on the cusp of a potentially monumental event in the life cycle of this star. But what could these changes in Betelgeuse signify? Are we witnessing the prelude to a cosmic spectacle of unimaginable scale? Betelgeuse, approximately 764 times larger than our Sun, is a stellar behemoth. Its colossal size is almost beyond human comprehension. Imagine a star so vast that, were it to replace our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its stellar embrace. This incredible size is not just a testament to Betelgeuse's physical attributes, but also speaks to its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase characterized by expansion and cooling following a life spent fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8 to 8.5 million years old, is relatively young in human terms but ancient in the context of stellar lifetimes. Its current red supergiant phase is the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that have transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Betelgeuse is a story of transformation, driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's distinctive reddish hue is another hallmark of its current stage. The red color is a result of its relatively cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is about 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at wavelengths that give it a red appearance. But this color is not just a visual trait, it provides clues about the star's physical condition and the processes occurring within its vast, gaseous expanse. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese writings suggest that around 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not just a detail in the annals of astronomy, but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another intriguing aspect. It's a semi-regular variable star, which means its light periodically waxes and wanes, and this variability is a characteristic dance of luminosity that has fascinated astronomers and skywatchers for centuries. Typically, Betelgeuse undergoes a 400-day cycle, along with a longer cycle that stretches about 5 years. These cycles have been documented as far back as 1836 by Sir John Herschel, and possibly even earlier in Aboriginal oral traditions. But what makes Betelgeuse truly enigmatic is not just its changing brightness, but its irregularity. Unlike many stars that follow a predictable pattern, Betelgeuse occasionally deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its colossal form. In a recent groundbreaking revelation, Betelgeuse captured the attention of astronomers and stargazers worldwide with an unexpected and dramatic change in its appearance, an event now famously known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to mysteriously dim. The star's dimming was so pronounced that it began losing its luminosity at an average rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Betelgeuse, normally visible to the naked eye even in light-polluted areas, became markedly fainter, a change noticeable even to amateur observers. However, there's one problem with trying to monitor the activities of Betelgeuse: the time paradox. When we look at a star like Betelgeuse, we are not seeing it as it exists in the present, but as it was in the past due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we perceive today left the star nearly 7 centuries ago. This time lag makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially peering into its past. The Betelgeuse dimming event served as a reminder of the inherent difficulties in real-time astronomical observations and the limitations of our understanding when dealing with the vast cosmic scales and the time paradox they introduce. The unfolding of Betelgeuse's celestial drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They utilized Hubble to analyze the behemoth star, a part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere. These observations offered a unique insight into the dynamics of a variable star like Betelgeuse, which regularly expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were heated partly by the star's turbulent convection cells. Further analysis of the Hubble spectra, taken at different points throughout 2019 and 2020, helped in measuring the movement of material in Betelgeuse's outer atmosphere. In particular, the spectra focused on magnesium-2 lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of about 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Betelgeuse and was the precursor to the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst. This mass loss was significant, especially considering that Betelgeuse, like all stars, continuously loses mass, albeit at a rate far greater than that of our Sun. The scale of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, about 725 light-years from Earth, adds to the intrigue, as any such explosion would be visible from Earth and provide a rare opportunity to observe a supernova up close. Yet, the question remains, what does this dimming event portend for Betelgeuse's future? Is it an indicator of an impending supernova, or simply a unique episode in the star's long and complex life? Several theories were proposed to explain this sudden change. One prevalent theory suggested a phase in the supernova explosion process, a hypothesis that gained traction due to the common belief that Betelgeuse is nearing the end of its life. Another popular theory implicated dust, possibly from the star itself, obscuring our view. Betelgeuse, like other red supergiants, is known to shed material, and it was thought that this material could form a dust cloud dense enough to dim the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. In-depth analysis using various observational methods helped unravel this mystery. Spectroscopic studies indicated a drop in Betelgeuse's effective temperature, suggesting that the dimming could be due to a large dark spot on the star's surface. This theory was supported by the observation that Betelgeuse's temperature dropped by at least 170 Kelvin around the time of the dimming, pointing to significant changes on its surface. In the end, the key to understanding this unusual phenomenon came from humankind's sentinel in outer space, Hubble Space Telescope. Hubble's observations revealed that the dimming of Betelgeuse was most likely caused by a significant ejection of hot material into space. This material formed a dust cloud that obscured a portion of the star's surface, effectively reducing the amount of light reaching us from Betelgeuse. The dust cloud was believed to have formed from superhot plasma, which erupted from a large convection cell on the star's surface and then moved through its hot atmosphere to the colder outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, were crucial in piecing together the timeline leading up to Betelgeuse's darkening. These observations captured signs of dense, heated material moving through the star's atmosphere in the months preceding the dimming. In December 2019, several ground-based telescopes also observed the star decreasing in brightness, particularly in its southern hemisphere. This material, which was initially more luminous than the star's normal brightness, eventually led to the formation of a dark cloud as it moved outward and cooled. The hypothesis was that this outflowing material and the resulting dark cloud caused the star's sudden dimming. The scale of this ejection is truly monumental, propelling Betelgeuse into an astronomical spotlight. The star expelled an estimated 400 billion times the mass typically released in a standard coronal mass ejection. This expelled material, believed to weigh several times as much as our moon, was a significant event not just for Betelgeuse, but for our understanding of stellar mechanics. But what does such an immense ejection of material mean for Betelgeuse and supernova theories at large? The implications for supernova theories are profound. Traditional understanding posits that red supergiants like Betelgeuse shed mass at a relatively steady pace before the explosive end of their lives. However, the scale of this ejection challenges this notion, suggesting a more turbulent and possibly unpredictable end-of-life phase for these stars. Could Betelgeuse be gearing up for its grand finale, a supernova explosion within the next few millennia? Recent studies speculate about the timing of such an event, suggesting that it could be sooner than previously thought, potentially in just a few tens of years. The concept of bow shock is another critical piece of the Betelgeuse puzzle. As this colossal star hurtles through space at approximately 67,000 miles per hour relative to its surrounding interstellar medium, it creates a bow shock, much like the wave formed by the bow of a moving ship. This phenomenon occurs as the star's outer layers interact with the interstellar gases and dust, providing a spectacular testament to the star's dynamic nature and its interaction with the cosmic environment. The study of this bow shock not only informs us about Betelgeuse's current state, but also contributes to our understanding of stellar evolution and mass loss processes. But what of the star's recent behavior? Betelgeuse's surface has been observed to cool and become less dense following the ejection event, leaving the star in an unstable state even years later. Hydrodynamic simulations suggest a connection between the star's convective activities, the mass ejection, and subsequent pulsation mode switching. This ongoing instability raises questions about the internal processes driving these changes and how they might culminate in the future. Moreover, the mass loss rate of Betelgeuse, as observed, is significantly higher than many other stars, hinting at a complex interplay of internal forces. The driven pulsation partly responsible for this mass loss is limited by the constant energy dissipation through shock heating and mass ejection. Such observations highlight the dynamic and somewhat unpredictable nature of Betelgeuse's life cycle, challenging astronomers to reconsider their models of stellar evolution. However, one might wonder, with all these dramatic changes, is Betelgeuse on the brink of going supernova? The question looms large in the astronomical community. While the timing of such an event remains uncertain, the recent unprecedented mass ejection has undoubtedly shifted the conversation, hinting at a more imminent end than previously anticipated. Theories now grapple with the implications of such massive material loss and what it means for the star's stability and future. Yet, as the astronomical community gazes intently at Betelgeuse, another cosmic event captures our attention and offers a vivid comparative study, the supernova SN 2023 IXF. This spectacular explosion occurred in the galaxy Messier 101, colloquially known as the Pinwheel Galaxy, situated a mere 21 million light-years away. Discovered in May 2023, SN 2023, IXF isn't just another supernova. It's the nearest one observed in recent years, offering an invaluable close-up of a star's cataclysmic finale. The discovery of SN 2023, IX, was no less than a cosmic coup. Koichi Itagaki, an amateur astronomer renowned for his supernova discoveries, first noticed this rapidly brightening speck on the outskirts of Messier 101 using a modest 0.35-meter telescope. Once he announced his find, the astronomical community sprang into action. Telescopes worldwide, from Earth's surface to the orbiting Hubble Space Telescope, swiveled to capture the unfolding drama of this newborn supernova. The ensuing race to monitor SN 2023, IXF's light curve, provided critical insights into the nature of the explosion and the environment around the doomed star. In the tumultuous month following its discovery, SN 2023 IXF's behavior was meticulously documented. The supernova surged from relative obscurity to dazzling peak brightness within a mere 5 days, only to embark on a more gradual descent, dimming by 0.03 magnitudes daily. Spectral analysis revealed a plethora of bright emission lines, a testament to the violent interaction between the expanding supernova shockwave and the gas surrounding the star. This wasn't merely a star ending its life. It was a massive star collapsing under its weight as its nuclear fuel was exhausted, the outer layers rebounding off the dense core in a spectacular core collapse supernova. But what makes SN 2023 IXF particularly intriguing is the dense shell of gas that enveloped it, significantly impacting the escape of the shockwave from the star's center. Two possible scenarios could explain this dense circumstellar material. Either a strong, steady wind had been shedding material from the star before the explosion, or the star experienced random outbursts, hurling material into space. In either case, it's estimated that the star lost up to a solar mass of material in the last 2 years of its life, indicating that its final moments were anything but serene. Identifying the progenitor of SN 2023 IXF has become a focal point of study. Through various methods and datasets, researchers have converged on a likely candidate, a red supergiant. So, by studying the details of SN 2023 IXF's explosion, including its progenitor's characteristics and the mechanisms leading up to its final detonation, astronomers can refine their models of stellar evolution and supernova mechanics. These insights directly inform our understanding of Betelgeuse's current state and its potential path to supernova, offering a clearer picture of what signs to look for and how to interpret the massive red giant's complex behaviors. But when will Betelgeuse explode into a supernova? Research from Japan's Tohoku University has suggested that Betelgeuse might currently be in the carbon-burning stage of its life, a phase that typically precedes the end of a star's life. The leader of this study, Hideyuki Sayo, posits that the star's core could collapse a few tens of years after the carbon is exhausted. Conversely, researchers from Hungary's Konkoly Observatory believe Betelgeuse is in an earlier helium-burning stage. Despite these differing views, there is a consensus that Betelgeuse is likely to be the next supernova in the Milky Way, although this event might not happen for another 100,000 years. Historically, observations of supernovae have provided invaluable insights into stellar deaths. The earliest confirmed record of a supernova, dating back to 185 CE, was observed as a bright star that took about 8 months to fade from the sky. Since then, several significant supernovae have been recorded, including SN 1006, the brightest recorded star ever to appear in our night sky, visible across various parts of the world, and SN 1054, which resulted in the formation of the Crab Nebula and was visible in daylight for 23 days. The most recent supernova observed in the Milky Way was SN 1604, studied extensively by Johannes Kepler. More recently, supernova 1987A in the Large Magellanic Cloud was observed within hours of its light reaching Earth. marking the first supernova detected through neutrino emission and observed across every band of the electromagnetic spectrum. These observations have been crucial in developing successful models of supernova behavior and understanding their role in star formation. So what if the night sky suddenly burst into a brilliant display of cosmic fireworks, captivating our gaze with the radiant explosion of a star? Imagine for a moment the once familiar constellation of Orion adorned with an unfamiliar blazing jewel. Betelgeuse, one of its prominent stars, transformed into a brilliant supernova. Could this awe-inspiring event impact Earth in any way? Betelgeuse's impending supernova is classified as a core collapse supernova, a type of explosion that occurs when massive stars exhaust their nuclear fuel and can no longer support their own gravitational collapse. Core collapse supernovae are among the most energetic and cataclysmic events in the universe. However, the most immediate and visible effect of a Betelgeuse supernova would be a spectacular light show in our night sky. The explosion would briefly outshine the moon and would be visible even during the day. Imagine gazing up at the daytime sky and witnessing a second, incredibly bright sun appear for a few weeks or even months. The event would be a breathtaking celestial display, captivating astronomers and stargazers alike. But as fascinating as the visual spectacle of a Betelgeuse supernova would be, its true significance lies in the scientific opportunities it presents. Supernova, particularly those of massive stars like Betelgeuse, are cosmic laboratories that offer invaluable insights into the fundamental workings of the universe. One of the immediate benefits of observing a Betelgeuse supernova would be the opportunity to witness the final stages of stellar evolution up close. When massive stars like Betelgeuse explode, they distribute elements forged within their cores, including heavy elements like iron, into space. This process is responsible for enriching the universe with the building blocks of planets, stars, and life itself. By studying the spectroscopic signatures and the distribution of these elements in the aftermath of a supernova, scientists can gain a deeper understanding of how stars evolve, fuse elements, and contribute to the formation of new celestial bodies. This knowledge is crucial for unraveling the history and composition of the universe. While the visible light from a Betelgeuse supernova would be dazzling, an equally intriguing aspect of the event is the emission of neutrinos. Neutrinos are subatomic particles that are notoriously difficult to detect because they rarely interact with matter. However, in the intense environment of a supernova, they are produced in vast quantities. These elusive neutrinos offer a unique window into the heart of a dying star,